Hello everyone, this is lecture 4 of vector space. Today we will discuss about linear sum of two subspaces. So, linear sum of two subspaces. What is linear sum? Now, suppose U and W be two subspaces of a vector space V, of a vector space V. Then linear sum of U and W, vector space V assume over the field F. Now the subset Q plus W such that U belongs to capital U and small w belongs to capital W is called linear sum of the subspaces U and V. Sorry, the subspaces U and W. U and W. Now the result arises from this that Q clearly subset of U plus W and also W subset of U plus W, where U plus W is linear sum of U and W, that is small u plus small w, such that small u belongs to capital U and small w belongs to capital W. This is denoted by U plus W. Now, U subset of U plus W. Why? Let alpha belongs to U. Now, since W is a subspace, therefore theta also belongs to W, where theta is the zero element. Alpha is equal to alpha plus theta. Therefore, it is belongs to U plus W because alpha belongs to U and theta belongs to W. So, alpha plus theta belongs to U plus W. This implies alpha belongs to U plus W. Here, alpha is an arbitrary element in U. So, for every alpha belongs to U, alpha belongs to U plus W. Therefore, U is subset of U plus W. Similarly, we can say that W is subset of U plus W because if alpha belongs to W, then theta, U is a subspace, so theta belongs to U. So alpha plus theta belongs to W plus U, that is U plus W, because addition is commutative. So alpha plus theta, that is alpha, also belongs to U plus W. And so W subset of U plus W. Now, there is a theorem that the linear span of two subspace U and W, this is a subspace of a vector space V. So, the linear sum U plus W is a subspace of V. So, proof. Now, a subset of a vector space V is a subspace of V if it satisfies the condition. Number one condition, alpha and beta belongs to U. This implies alpha plus beta belongs to U. And number two, C belongs to field and alpha belongs to U implies C alpha belongs to U. Then U is said to be a subspace of V. These are the two conditions for a subset U of V to be a subspace of V. Now, suppose S is equal to U plus W. Theta belongs to U and theta belongs to W because U and W are two subspaces of V. This implies theta belongs to U plus W because theta plus theta is equal to theta. So, U plus W is non-empty. Non-empty. Now let alpha 1 and alpha 2 belongs to U plus W. So alpha 1 is equal to u1 plus w1, where for some u1 belongs to capital U and w1 belongs to capital W. Similarly, alpha 2 is equal to u2 plus w2, where u2 belongs to capital U and w2 belongs to capital W. We have to prove that alpha 1 plus alpha 2 belongs to u plus w. So alpha 1 plus alpha 2, this is equal to u1 plus w1 plus u2 plus w2. This is actually equal to u1 plus u2 plus w1 plus w2, because addition is associative. This is actually belongs to u plus w, because u is a subspace of V. So u1 and u2 belongs to capital U, implies u1 plus u2 belongs to capital U. And also, as w is a subspace of V, so u1 plus w1 plus w2 belongs to W, implies w1 plus w2 belongs to W. So this belongs to u plus w. So alpha 1 plus alpha 2 belongs to u plus w, for all alpha 1 and alpha 2 belongs to u plus w. Now let's see B a scalar belongs to capital F. C alpha 1, this is equal to C into u1 plus w1. This is actually equals to C u1 plus C w1. Then by the similar manner, since U is a subspace of V, so C u1 belongs to capital U and W is a subspace of V, so C w1 belongs to capital W. So this sum belongs to U plus W. Therefore, C alpha 1 belongs to U plus W, for all C belongs to F and alpha 1 belongs to U plus W. Therefore, we can say that U plus W is a subspace of V. Now here is a theorem that the subspace U plus W is the smallest subspace of V containing U and W. We have already seen that U plus W is a subspace and also U plus W contains U and W both. So here we have proved that, here we can prove that. So here we can prove that U plus W is a smallest subspace of V containing U and W. Now let P be any subspace of V containing U and W. We prove that to prove U plus W is subset of P. And then we can say that U plus W is smallest subspace because it is contained in any subspace of V containing U and W. Let alpha belongs to U plus W. We prove that alpha belongs to P. Since alpha belongs to U plus W, then alpha is equal to U1 plus W1, where U1 belongs to capital U and W1 belongs to capital W. Since P contains U and V both, so U subset of P and W subset of P, therefore U1 belongs to P and also W1 belongs to P, because U1 belongs to capital U and W1 belongs to capital W. So since P is a subspace, since P is a subspace. Therefore, U1 plus W1 belongs to P because U1 and W1 both belongs to P. This actually means alpha belongs to P. So alpha belongs to U plus W implies alpha belongs to P, and it is true for all alpha belongs to U plus W. So U plus W is a subset of P. Therefore, U plus W is the smallest subspace of P containing the subspaces U and W. So proved. Now here is a result that let P be a vector space over a field F and let alpha belongs to V, then the set W is equal to collection of all C alpha where C varies in F forms a subspace of V. So let's start the proof. It is very easy and clear. Case 1, alpha can be theta. So first we consider the case alpha is equal to theta, then W is equal to singleton theta, which is trivial subspace of V. So from this, clearly W is a subspace of V. Subspace of V. Now case 2, alpha not equal to theta. Then first W is non-empty as alpha is equal to 1 into alpha. This is belongs to W, where 1 is the identity element of A, capital F. Second, let C1 and C2 belongs to capital F. Then C1 alpha and C2 alpha belongs to W. Now C1 alpha plus C2 alpha, this is equal to C1 plus C2 of alpha, which is belongs to W. Since C1 and C2 belongs to capital F, it is implies C1 plus C2 belongs to capital F because F is also a vector space. Therefore, addition of two elements of W belongs to W. Now, number 3, let P be a scalar and C1 alpha belongs to W. Then P C1 alpha, this is equal to P C1 of alpha, which is belongs to W. Since P C1 belongs to F, since P belongs to F and C1 belongs to also F. So, P belongs to F and C1 alpha belongs to W implies P C1 alpha belongs to W. Therefore, from 1, 2 and 3 we can say that W is a subspace of V. Subspace of V. So here we take W is equal to C alpha such that C belongs to capital A. If we take W dash is equal to C alpha plus D beta such that C and D belongs to capital A, where alpha beta belongs to capital V, then also similarly we can prove that W dash is a subspace of V. Subspace of V, and we can continue this process. Similarly, continuing, we can say that W is equal to C1 alpha 1 plus C2 alpha 2 plus C2 CR alpha R such that Ci belongs to capital F, where 1 less than equal to I less than equal to R. This is also a subspace of V, where alpha I belongs to V, 1 less than equal to I less than equal to R. This W is a subspace, and alpha 1, alpha 2, alpha R is called the generating set of the subspace W. Now, from these we can find a definition: linear combination. Linear combination. Let V be a vector space over a field F, and alpha 1, alpha 2 up to alpha R belongs to V. A vector beta in V is called a linear combination of the vectors alpha 1, alpha 2 up to alpha R, if beta can be expressed in the form C1 alpha 1 plus C2 alpha 2 plus CR alpha R, where Ci belongs to field F, 1 less than equal to I less than equal to R. Here is another theorem that let V be a vector space over a field F and let S be a non-empty finite subset of V. Then the set W of all linear combinations of the vectors in S forms a subspace of V, and this is the smallest subspace containing the set S. Let S is equal to alpha 1, alpha 2 and alpha n, where alpha I belongs to V for all 1 less than equal to I less than equal to n. So W is linear combinations of the vectors in S. Therefore, W is equal to C1 alpha 1 plus C2 alpha 2 up to Cn alpha n, where C1, C2, Cn belongs to field F. First, we prove that W is a subspace of V, and second, we prove that W is the smallest subspace containing the set S. Let W1 and W2 belongs to capital W. Then W1 is equal to C1 alpha 1 plus C2 alpha 2 up to Cn alpha n, where Ci belongs to capital F for all 1 less than equal to I less than equal to n, and also W2 is equal to D1 alpha 1 plus D2 alpha 2 plus Dn alpha n, where Di belongs to capital F, 1 less than equal to I less than equal to n. So W1 plus W2, this is actually equals to C1 alpha 1 Cn alpha n plus D1 alpha 1 up to Tn alpha n. This is equals to C1 plus D1 alpha 1, C2 plus D2 of into alpha 2, and up to Cn plus Dn alpha into alpha n. This is actually belongs to W, since Ci and Di belongs to capital F implies Ci plus Di belongs to capital F field. Now let P belongs to field F and W1 belongs to capital F. Then P into W1, this is equal to P into C1 alpha 1 plus C2 alpha 2 up to Cn alpha n. This is equal to P C1 alpha 1 up to P Cn into alpha n. This is belongs to W since P into Ci obviously belongs to the field F, where each Ci belongs to capital F. Also, alpha 1 belongs to W always. So W is non-empty. Thus, W is a subspace of V. Now we prove that W is the smallest subspace of V containing the set S. Let P be any subspace of V containing S. We prove that W is subset of P. Let Xi belongs to W, then Xi is equal to C1 alpha 1 plus C2 alpha 2 up to Cn alpha n, where Ci belongs to F. Since A is subset of P, therefore alpha 1 alpha 2 alpha n belongs to P, and also Ci C1 C2 up to Cn belongs to capital F. And P is also a subspace. So C1 alpha 1, C2 alpha 2 up to Cn alpha n belongs to P. P is also subspace. Therefore, C1 alpha 1 plus C2 alpha 2 up to plus Cn alpha n also belongs to P. This implies Xi belongs to P. So, Xi belongs to W implies Xi belongs to P, that is W subset of P. And this is true for any subspace of V containing the set S. So, W is the smallest subspace. Containing S. Now, linear span of S, the smallest subspace containing a finite set S of vectors of a vector space V, is called linear span of S and is denoted by Ls. Ls is said to be generated or spanned by the set S, and S is said to be generating set or spanning set of Ls. Now, if S is equal to phi, then linear span of S, this is equal to singleton theta, where singleton theta is the intersection of all subspaces containing phi. And if S is equal to a non-empty finite set, that is alpha 1, alpha 2, alpha n, then Ls is the linear combination of the vectors alpha 1, alpha 2 up to alpha n in S, all possible linear combination of the vectors alpha 1, alpha 2, alpha n. If S is a non-empty finite set, then Ls is equal to this, and if S is equal to empty set, then Ls is equal to singleton theta. That is all for today. Thank you so much.